the idea that correlation does not imply causation, is that only something that statisticians are very comfortable with, or is that a common turn of phrase? Like, is that a publicly common turn of phrase, regardless of people's ability to actually apply that concept?
I feel like it's super common. Um, yeah, even I mean, as far back as when I was a bio major, I'm sure even in high school, it's just a mantra, right, that gets
Yeah.
thrown around. And what I like to remind people of is, these sort of mantras are, I don't know if platitudes the right word, these kind of like hackneyed phrases that get thrown around a lot. There's a cognitive reason they get thrown around, right? It's like for a lot of these, they're reminders because we suck at them. So there are things that we've developed little phrases around to remind us. And correlation doesn't imply causation is one of those. But in my experience, it gets diluted to correlation is not causation,
Hmm.
which, colloquially, that's fine. You don't have to be as precise as saying implies causation. But yeah, so I feel like it's fairly widely known. And then to to get to folks who really start to dig into it, then it gets real narrow real fast.
Hey everyone, welcome back. Today we have Eric J. Daza for, I believe, his second interview with us. Is that true? Is it his second interview?
It's true, yeah.
Okay.
Second, yep.
Yeah. The problem with actually interacting with people and talking to them like colleagues outside of interviews is that you forget how often you've actually had like podcast conversation versus just a normal email conversation or a normal catching up conversation. But yeah, just so we're gonna be talking about the Andrew Gelman and Aki Vehtari paper on important ideas. We're gonna be talking about some causal inference, and maybe just to get started off, three questions begin. One, are you happy to be back on the show?
I am very happy to be back on the show. Thank you. Thank you for
Very good.
having me.
I'm happy to have you back as well. Um, Question number two, what does the J in Eric J. Daza stand for?
Oh, I love it. I haven't been asked this in a long time, and if you've ever watched The Simpsons, you know the answer.
I do know
It's
the answer.
which is
Stands for J.
that's right.
Very good.
And it does.
All right. And finally, if you had to name the top eight most important statistical ideas in the past 50 years off the top of your head, what would they be?
Oh my gosh, eight?
Yeah,
Woo.
eight.
Okay, well, I mean, causal inference is a big one.
Hmm.
I would say counterfactuals. I'm going to split it up: counterfactuals and causal inference, directed acyclic graphs and causal inference. Um, uh, I'm just so biased towards this, but I'll also say actually, seminal work in N of one trials. This is also, it's showing my bias, but I say that because it's moving towards using those methods to analyze huge streams of single time series, multivariate time series wearable data. So that's why I think it's important. Well, I got the three. I would say it's really just a lot of the ideas in this article. I know that's kind of a cop out, but I liked a lot of these. I can start reading them off, but we're going to get into that.
Yeah,
Um,
honestly, I would have accepted if you just like picked up the paper, put it right in front of your face, and said the top eight most important statistical ideas, in my opinion, are the following in order: counterfactual causal inference,
right.
bootstrapping and simulation-based inference,
Hmm.
over-parameterized models and regularization, Bayesian multi-level models, so definitely Andrew Gelman network here.
Yep.
Um, Generic computation algorithms, that's a nice one.
Yeah.
Adaptive design analysis, robust inference, and exploratory data analysis. Those are the eight that I would have selected. Um, what does the paper say?
Let's see.
How about that? It looks like those eight in that exact same order. How about that?
Look at that.
Yeah, look at that. Cool.
Wow. That's
Yeah.
a statistically significant finding.
That's the most statistically significant of findings. Yeah. Great. So, actually, that actually brings up a point. One thing that I'm surprised that they didn't mention here, the real most important statistical idea of the last 50 years
Hmm.
is the major advancements that we made as a profession on p-value hacking. Of
Mm.
everything we've done really well, we've
Hmm.
gotten really damn good at p-value hacking over the last 50 years. Like, I don't think the scientific community has been any better at p-value hacking than it is at this very moment. Um, Yeah, it's just available to everyone. My cat, dragged some statistical significant out from under the couch earlier, just playing with it,
Hmm.
letting it sort of escape and then catching it again.
Yeah.
So a
Yeah.
cat don't do that, and then it let it go, and then some sociology professor swooped in and took it and ran off to probably Duke University to do
There you go.
something with it. Yeah, but
Yeah, I
um,
think in ecology that's called the catch and release p-value method, right? Yeah. Catch and release
yeah,
yeah.
yeah, you tag it and you see if it comes back again. Um,
I
yeah,
love it.
cool. Yeah,
But you got to throw it back in the same pond. So
yeah,
what
definitely.
you got to do is you got to double, triple dip in the same pond.
Yeah,
Right?
yeah.
Yeah,
And
switch
by
it.
pond we mean cesspool.
That's
um, but yeah. So basically, I'll pop the picture of the article up, but it's Andrew Gelman and Aki Vehtari, and it's what are the most important statistical ideas of the past 50 years, and front and center, the very first one that they have listed is counterfactual causal inference, and
Woo!
I thought you'd be the guy to bring on for this, because I know nothing and you know something, and that is a very good power sort of dichotomy to have on this. So
Nothing, something.
yeah, so maybe I can just pop out this that here's what they say. They go on. This is basically first page, uh, first subsection where they say, um, the key idea is that causal identification is possible under assumptions. Oh, I'm sorry. No, here it is. It's the idea of bridging the gap on one hand between naive causal interpretation of observational inferences, and on the other, recognition that correlation does not imply causation. Um, and I think that's a pretty tidy summary. One thing I actually want to ask is the idea that correlation does not imply causation. Is that only something that statisticians are very comfortable with, or is that a common turn of phrase? Like, is that a publicly common turn of phrase, regardless of people's ability to actually apply that concept?
I feel like it's super common. Um, yeah, even I mean, as far back as when I was a bio major, I'm sure even in high school, it's just a mantra, right, that gets
Yeah.
thrown around. And what I like to remind people of is, these sort of mantras are, I don't know if platitudes the right word, these kind of like hackneyed phrases that get thrown around a lot. There's a cognitive reason to get thrown around, right? It's like for a lot of these, they're reminders because we suck at them. So there are things that we've developed little phrases around to remind us. And correlation doesn't imply causation is one of those. But in my experience, it gets diluted to correlation is not causation,
Hmm.
which, colloquially, that's fine. You don't have to be as precise as saying implies causation. But yeah, so I feel like it's fairly widely known. And then to to get to folks who really start to dig into it, then it gets real narrow real fast.
Hmm.
Yeah.
So I guess what was interesting about this is that they say that the one of the main benefits, one of the main sort of developments is that we become more precise, so there's more precision on the assumptions required for causal inference. So the idea is that we had these methods, and we've become now precise on what is necessary to attach these correlational relationships to causational relationships. Is that a good way to start with this?
Yeah, I think so. This the phrase here I'm reading it to a much more precision on the assumptions required for causal inference to me is a key phrase because Gelman and Vehtari mentioned this later on. Causal inference, those methods largely are concept and theory based methods. They're not so much coding or on that end of things. It's really classically about what are the assumptions in play for you to make these conclusions, but how you do the mechanics of it doesn't really change. You still fit a regression model, you still do those things, but because we're able to say more precisely in mathematical terms what the assumptions are, we can then apply those assumptions to generate new math logic based approaches to do the adjustments that we need.
Yeah, no, that's it. That's a super interesting bit because one thing that I've mentioned this a few times, actually, maybe even with you, where And it actually comes up on like the very next line that they mentioned, where say different methods for causal inference have been developed in different fields. And what I think is interesting is, as you talk about, you can do the same computation, use this exact same model, but whether or not you can make causal inference is heavily based on the assumptions. And what I think is interesting is that when we usually inflict stats on early stage students, the discipline in which you learn your statistical models comes with those implicit assumptions about the data, and no one bothers to specify it. So effectively, you'll have the econ student with certain assumptions, and that is what like in linear regression encompasses all those ideas to them. And then when they go into biology, same model, same literally the same mathematics, same computation, but those assumptions aren't there, and they might wind up sounding like a fool.
Yes, I'm gonna give a soft abstract example
Yeah,
of something like that where, and this is where working in data science is really it's really fulfilling and also challenging, but I don't want to emphasize the challenging part. It really is. I do derive joy from this, but seeing those assumptions, like you said, become unearthed, where you're coming from a field where your regression was causal because you were doing all the experimental manipulation and you know how those models will fit. You internalize that because it's very intuitive as a human to see causation, and it's not that intuitive to see correlation. So then you come into like the data science field, and now you're dealing with variables where you didn't experiment with them. You didn't mechanically change the X, right? But then because there's a client deadline to meet or there's some other pressure, those assumptions just get assumed. They get jammed in, and it takes a little more work to back it out and say, oh, those don't apply anymore in this situation. So yeah, totally get that, and
yeah.
I've seen that at play.
And do you think so for example, I really like the idea of where if the baseline is considered, you're actually experimenting, you're controlling for the data.
Hmm.
And I think what is interesting is in so many of statistical fields, our basis is from experimental ideas. R.A. Fisher was an experimentalist. Like he experimented and he designed methods around his experiments. Who else do we have? Um, Gertrude
Uh,
Cox, for
yeah.
example, was about designing experiments. Massive experiments that took up real big fields, but it was around experimental design. And so
Hmm.
I think that uh, uh, the other famous David Cox, he was also designing some experiments. A lot of his data also was observational, but again, there's an experiment. Well, I mean, his that one is tricky to unpack. I'm not going to step into that one because that one would take us too long. But yeah. So can you talk a little bit more about this way in which there's the experimental design and what sort of that leads to, and then we'll next talk about when the gloves are off and we're talking about observational stuff.
Right. Yeah. No, that's great. I was going to bring up that also that split bucket kind of view, right? Where it's artificial because there's a lot of gray in between, where you'll have an experimental design that then has observational components. Because, for example, in a drug trial where you assign treatment to control, that's great, but then you have folks that don't adhere or don't engage, mostly due to a lot of times due to the design of the trial, or the drug is too hard to take the way it was meant to be, whatever. Now you're starting to creep into observational land because you now have to account for phenomena that arose in the process that you then have to deal with at the end, and that becomes more observational. Um, and you slip into the realm of effectiveness studies in pharma, where now it's out in the world, and you didn't control who's taking what. So now that's kind of the fully observational side of it. But yeah, a lot of those the two big buckets are those, and these days the experimental part is thriving in fields outside of clinical stats and health, right? Because they have to do with yeah, we are experimenting, but we're doing it on a massive scale across so many different people or units that now we have to account for all the interference that happens between those units. Um, and that's where causal inference is sort of thriving in this new direction that it didn't before because they didn't have experiments at this scale. Not like at Fisher's theory.
Yeah.
It's 100 units, maybe a few hundred at most.
Yeah. So maybe just to provide a really concrete example, one that probably we are going to be familiar with, and probably a lot of the listeners. I'm familiar too, given that I tend to bring up a lot of the same examples because I'm essentially a one trick pony. Um, but like, we can have some type of clinical intervention that, let's just say, requires you to take a pill at 9 a.m., 12 p.m., 3 p.m., 6 p.m., and 9 p.m. So you take a pill. Hopefully, that's what, 4 or 5 times a day on
Yeah.
the hour, and you do that. And I don't know. Let's just really throw a loop in this one and have them also measuring their blood pressure at the same time. Um, that is too much to ask for the vast majority of clinical patients, particularly that the people who need to go into clinical trials are not the type who can adhere to the type. They typically aren't the ones who can adhere rigorously to those type
Hmm.
of daily regimes. And so effectively, no matter how you randomize and control and stratify, you're still going to be adding an observational element because you're not going to be truly controlling for treatment as well as you think you can. And to whatever extent you can, there's still going to be all these other effects that you can't control. Family history, their drinking habits on top of that. And so there's effectively, I really like it how it's a continuum on how close you are to an actual experimental design versus an observational trial. And personally, when I also believe that there's probably a large amount of personalized effect size in these. So effectively, the effect size is a single. Honestly, I don't want to sound too basic, but I honestly believe that the effect size is probably a distribution over each individual. Um, and that it's a conditional distribution too, as you like to point out. It's a conditional distribution on that individual. So there's a lot of variability even what that individual has, and then we're trying to stack these things up and try to create population-based estimates. Um, it's just impossible to control for. So we try.
Well, really quick, I won't. I definitely won't object to that Bayesian connection because it's also a very N of one concept that everyone has a distribution of effect sizes for a given effect. Like that's a lot of my work that I do is what's the average individual treatment effect taken over multiple instances. And the reason it ties in so well to a lot of the Bayesian work is because guess what? A lot of the common approaches to aggregating across people, even with N of one studies, is through multi-level modeling because every person's their own study. So there you go. How do we model that? Well, every person has their own intercept and it has some variation around it from instance to instance. Voila! Now you have a more structured, aggregated N of one. So yeah, totally makes sense to me as a concept.
Yeah. Um, on this, one of the things that is that he mentions, about, or they mention, is that on the issue of that, a lot of this can actually get boiled down to missingness, and essentially you consider it to be a missingness problem. That causal inference comes down to missingness. And what's interesting about this is I'm actually one of the papers in the philosophy of data science journal section that's coming up is essentially, it's meant to be a casual introduction to causal inference, and the student at Duke who's writing this paper um, made this very same analogy right off the bat, and as someone who doesn't know very much about causal inference, oh, that's a really cool way to describe it, and he gave an example why I didn't understand it. But can you flesh this out? Why is this a data missingness problem? And then to whatever extent that isn't good enough of a descriptor, we can cover that later. But why is it good enough to call this, causal inference as a data missingness problem?
Yeah, that's a great question. I actually have, surprise, surprise, I have developed somewhat strong opinions about that view of it. But to explain the mechanics, a lot of the theory in potential outcomes or counterfactual based causal inference came from Rubin and the group of people around that camp. And that camp, in my basic understanding, I could certainly be wrong here, developed missingness methods and causal inference methods around the same time or with the same, knowledge roots, epistemological roots, basically. And the idea was that Glenn, for example, can we can give him a treatment or control, but we can only give him one or the other. But in theory, it's not a far stretch to say there are two potential outcomes for Glenn: one under if he gets treatment, one under if he gets control. What then got to be called the fundamental problem of causal inference by I don't know if it was Rubin, and I think it was Holland, somebody I'm forgetting, um, is that we can only observe one of them. The other one is perpetually forever missing. Like we can't ever observe it. And so now you have missingness language in there. So the idea is the other potential outcome is a counterfactual because it's counter to fact of what you actually do observe. And there's your missing data framework. And then it's like, okay, we'll have at it. If that's missing data, then we can use missing data methods to try to estimate, population averages for all of the potential outcomes under a treatment or a control, just even within a clinical trials participant pool.
Mhm. And do we have those analytical tools off the bat? So the moment this is now formulated as a missing data problem where, there's the Glenn getting the treatment that he does eventually get, and then there's the Glenn who doesn't, and then there's the Bob getting the treatment that he gets, and
Mm-hmm.
then the treatment doesn't, and then the Ross getting the treatment he does, and then the one who doesn't. Um, so we have that. Is that the actual stack of data? So essentially, for every patient, you'll have like double, and then if you even have even more treatments, you'll have even more than that.
That's exactly it. Yep.
Okay.
And the methods that have been developed around that are pulled from survey sampling because in survey sampling, the missing data are the people who aren't in your sample. So we want to extrapolate from our sample to the rest of the population based off of our known sampling probabilities into our sample. And then, aha, that's where the connection is. Now we have these things called propensity scores, which is directly pulled from survey sampling probabilities.
Oh,
And here,
okay.
instead of a population, you have a population of everybody's treatment potential outcomes or a population of their control potential outcomes. Then you apply that method and you have all this stuff in propensity scores now. So
Hmm.
yeah, yep.
So, so cool, cool. So basically, in that, I think that's an interesting. It's a theme that they talk about later in the
Mm-hmm.
article, where effectively a lot of these things are they go from being they mentioned like a taste or a philosophy to the advances come from helping to sort of quantify and make these things very precise. And then by bringing that precision in, it allows us to bring in other methods from other fields, the other realms of statistics to bear on that. So now we have propensity scores on these things. Um,
Yep. Yep.
and
Yep.
we have all the mechanisms that go with that. So effectively, then it's a plug and chug. And then we can go back to unthinkingly applying statistical methods yet again.
That's right.
Yeah, perfect. Cool. So, but on the issue of actually thinking about these things, you said that you had a strong opinion on the representation of these as a missing data problem. Um, so what is your opinion? Because obviously, we like to get the flavor of what's out there.
Sure. Yeah, I don't it's not an opinion so much about if I agree or disagree so much as how useful is that concept. And it's more something I like to think about and play with. It comes from the quick background here is I started off writing my dissertation as a causal inference dissertation, but my advisor and I, a year in, realized we didn't have the sample size to do it. We had a much larger sample, but by the time we looked at the actual analysis sample, it was like just maybe just over 100 people, and we couldn't do what we had wanted to do. So we pivoted and turned it into let's deal with the missing data in this longitudinal sample. And so because of that, I got really familiar with actual what it meant for data to actually be missing and to use basically the same method to deal with that as you would to recover a potential outcome distribution. Um, and so for me, it's there's a very deep difference between this is actual missing data and this is um, an analogy of missing data. And so it's I don't I was talking to a colleague about this who is not in statistics but is very interested in these methods, and they were saying, well, yeah, I mean, I get that. I don't know how many people actually believe that you're necessarily there are two actual potential outcomes and one is missing in a parallel universe. But you see, once you use the word parallel universe, it gets really interesting to think about philosophically, and even dipping into some of the physics work on parallel worlds and how to interpret was it the Copenhagen interpretation or whatever it is of um, I'm starting to spin off into who knows where, but
The unknown
it gets
territory.
philosophical.
Yeah.
Yeah.
Cool.
So that's it. That
Yeah, actually, I was one of the things I was wondering about this is, are there ways to bring in external data, so extra data to help with these, for example, propensity scores, and to essentially, can you enrich your own data set um, with external information to help you get a better idea about what these propensity scores are and better ways to essentially fill in the gaps for missingness?
Yeah,
And is
you're
that,
kind of
yeah,
yeah, you're kind of teeing up an idea, one of the connected ideas here, which is It's called transportability. In my basic understanding, it's just a word for generalizability of your causal findings. So if you have like observational data and you adjust it using propensity scores to see what if X had been randomized, that's essentially what observational causal inference methods do. Statistics. They try to replicate randomization that didn't happen. Um, you have to make some strong assumptions to do that, but it's doable. Um, if you can do that, then does my causal effect, does it generalize to this other population? So what you're talking about is the other way, where it's and work has been done on this, where you would take something a finding from a clinical study where they did randomize X, and then say, okay, well, if this was the effect size in this study sample, how does it translate to my current sample? It's maybe observational. It's out in the world. With X wasn't randomized, but I know these like demographic features, and I can adjust to sort of match what was in the clinical trial. So there's uses of combining data sets to get a better inference causally for like what's in front of you. Yeah.
as a little bit of a side note, and this could be a separate conversation, but you're here, so we might as well see where it goes. When people
Whoa,
talk
that's a
about
bad way to go.
yeah, but like when people talk about generalizability, especially in medical care, one of my pushbacks is that, and people say, oh, we need these more generalizable algorithms, we need these more generalizable warnings and things like that. My main pushback is, no, you don't. No one actually wants a generalized algorithm. What they want is a specific algorithm that doesn't tell them how it affects them or their patient. They want a highly personalized one. And when they say generalizable, what they really mean is only generalizable enough so that it works on the one person I care about or the one set of patients. Thoughts, comments on that idea?
Oh yeah, I mean, don't yeah. Well, this is bad to get me started on since this is my direct line of research. But yeah, that's what I do at Stats of One and what N of One methods and within individual methods are all about. What is the if you are a population of different instances at different points in time, what are the general patterns in that population, and how can we extrapolate from the data that we observe on you for the short amount of time to what could be the general trend for you? Um, and then it's gravy if it happens to work across different people, because then an organization can start to become more efficient about developing an intervention that actually works fairly consistently across different people. I think honestly, I feel like that is. I don't want to. I don't want to speak for people long gone into the past, but I feel like that's the more that has been the more desired and intuitive target this whole time. It's just that we didn't have those methods or that data at the time. But I'm going to walk that back a little bit and say like statistics from Statista and the German for state was meant for administrators, dealing with populations. Um, but very much in the clinic, yeah, the population is the patient or the athlete if you're in fitness, you're a sports team, Yeah. See, I
Yeah.
stopped myself. Then
No,
keep
yeah,
going.
very, very good. It's a admirable self-control there. I'm just gonna keep going on this topic. So yeah, I see your self-control and raise you a. We're gonna keep going.
Oh,
Yeah.
okay.
So because one of the things that for my work in personalized time series modeling is that I put so much effort into the inference side of essentially what algorithm can I design that's really good at probing at personalize an individual patient's data to actually understand, for example, the personalized dynamics. And I had the extreme benefit of dealing with very high frequency data. So I was sampling a lot from an individual patient across multiple channels. They were confined to relatively similar types of clinical scenarios. Um, but I think the main thing is I had so much data there that I could actually design an algorithm that was really good at just probing at, hours turns into days of data for
Yeah.
each individual patient and really learning those things. And what was nice is that at the end, it was a generalized algorithm but it was a generalized algorithm that really learns how to probe the personalized bit. And then once we learn that, then you can really exploit the benefits of an algorithm that understands the person very well. So essentially, we have one algorithm that learns, and then it proposes the model. And that second model, then it knows the patient pretty darn well in most cases. And that seemed to work well. So is that, but I guess the issue is that there, I wouldn't call that a uniquely statistical piece of work. It was more of a piece of engineering,
Mhm.
where in non-statistical in many ways, where effectively the first part of the algorithm was literally just trying to figure out how to construct one of these things, and then there's only a statistical model that came out after that. So I guess I don't know. It doesn't have that nice, clean, sexy, probability statistics only type approach to it. It gets into the weeds. Well, what are your
No, I
thoughts on
think
that?
that
Yeah.
that touches on actually one of the themes in the article. See what I did? Brought it
Mm-hmm.
back.
Yep.
I suck at that, so I'm always proud of myself when I can do that. But one of the themes was how modern statistics is really this amalgam now of it's statistics combined with machine learning or computer science, where we're starting to blur the lines between like estimation of a population quantity versus generalizability and prediction, because the flavors are very similar. They're very they're very similar in goal. But this would be more of a prediction flavor, where it's like we just need something like that's good enough for this one person, and it works fairly well from time to time. And what's good enough isn't like one fixed intervention or one fixed tool. It's an adaptive algorithm. It's an adaptive tool that adapts over time to help you figure out what your patterns are as they shift over time. So yeah, so now we're going into like an engineering type of framework using some statistical ideas. So yeah, I think it speaks very much to what they were talking about as well. Um,
Yeah, it actually fits in a few places because they have the generic computation algorithms.
mm,
And one of the interesting things there is that they talk about how, especially for example the optimization versus maximum likelihood
mm,
approaches, um, is just one of the examples where they talk about how we took these mathematical methods from other areas of applied mathematics, or even theoretical mathematics, and apply them to the problem at hand to have an inference. And one of the nice things is that if you can disconnect the actual statistical model from the computation required for inference over that model, it's very useful because, oh, think about not having that, or effectively every time you have a new proposed statistical model that you need to hand construct the inference to fit those parameters. That's a thing. I mean, that's not just like, oh, we're talking about something that was, back in the heyday. That one of the main reasons I think why a lot of young statisticians have so much trouble learning models quickly is because each model actually comes with a bespoke statistical inference process that they would
mm,
have to learn for those.
mm.
Um, and seeing those things get pulled apart, for example, like with probabilistic programming and things like that, where you have these two separate things, and now you only have to learn the model, and the inference will handle itself. Deep learning, I think, is another one of those great things where effectively you can flip out the architecture, so the actual deep learning architecture. But you can always rely on Atom in the end to pull you
Right.
through. Is there's something to be said about that I think um I don't know, like I'm kind of dumb, so it's like that was something that always sort of caught me up when I was trying to learn new model after new model, learning that inference step and really understanding why it worked. Um, but yeah, I thought that was interesting.
Yeah, super quick note on that.
Yep.
This is a side note to the side note, but I think that feel like the statistical equivalent on that, not coming up with like a so you were saying like yeah, like there's a different model and then there's like a bespoke algorithm underneath that actually conducts the inference for the model, et cetera, et cetera. I feel like there's in statistics like this. I was just talking to another colleague about this, but mathematical statisticians have really keyed in over the years on the exponential family of distributions, because it's the one model that you twiddle it this way, now it's a normal. Twiddle it this way, now it's a gamma. Twiddle it this way, now it's Poisson. So that was their version of having like a one-stop shop conceptually, that if you can build maybe an inference engine for this model, well, because mathematically it's related to this one, it in theory literally shouldn't be too much of a lift to do the inference for this other one because we're just changing knobs on like the one box. The trade-off is that that's great. They're super well characterized. Are they realistic?
Yeah,
Yeah. So,
yeah. And that's not to knock the exponential family. Like the exponential
oh
family
yeah.
are like chipmunks. Like they get it's like no, that can't be oh yeah, that is in the exponential family. Or there are some surprising things there. Maybe my intuition is pointing that, but I've always been surprised where the exponential family can get into.
Yeah.
But yeah, but uh, yeah. So I don't know. Maybe back to the paper. But honestly, I thought that this was useful. I liked where it goes because it does actually hit on a lot of these things. So we talked a bit about the data missingness representation. Um, what are there alternative representations to this data missingness problem? What are other ways that you might look at this?
Yeah. Well, so this is kind of, you can see the different ways of looking at it by noticing the big sets of methods that are out there. So one of them is propensity score methods, and so that uses this missing data concept. Another approach, and underneath, I know somebody's going to slam me. It's like, oh, they're all missing data concepts underneath. But anyways, another approach, because I'm not that smart, is the G computation methods or G formula methods, which I like using. They're also known as the backdoor adjustment formula methods from Pearl's CS camp. And the idea there is that it's not that there's necessarily a missing counterfactual, but it plays very well with that concept. The idea is that you fit your model just like you do for an observational study, but in a randomized study with X, you've randomized it. So the connection between X and anything that happens before X probabilistically is gone since in theory, you've randomized it independent of everything upstream. And that's what gets you this estimate of a causal impact. Um, so statisticians are like, okay, well, if that's the case, that's how the map looks probabilistically. What if we do that with observed data where there might be confounding? So everything upstream of X might be impacting X, it probably is, and it might be impacting Y. What if we take that data and we adjust it such that we take away that error? So we pretend like we randomized X. Um, and the way we do that is we do some reweighting, basically. You still have there's strong assumptions. You need to know everything that confounds, everything that affects X and Y, blah blah blah. But if you have that, then the idea is you can still. So I like it because you can fit this fits really well into like data science and machine learning because it's like, look, we're still fitting your machine learning model. We're still fitting. It's the same thing, and this is an adjustment that happens after that, after you fit it, that pretends like the X you're interested in was randomized. So essentially, mechanistically, it's just a reweighting as if you would see if X were randomized. But it's a smoother transition between causal inference and statistics and machine learning, in my opinion, because in the pipeline of work, there's very little change. You're still doing the exact same thing you've been doing. The only add-on is now we're going to reweight them versus propensity scores where you have to change what your key model. Your key model is now modeling X, and it's a classification problem versus the thing you were modeling initially. So now I've added one more step. With the G formula method, you're adding like an adjustment afterwards. So anyways,
Yeah, no, that's interesting. So just to summarize, effectively, this G formula method does not affect your workflow, um,
mm-hmm. Yep,
as
exactly.
much, or I guess I mean it still does some, but effectively it doesn't affect the fundamentals of your analytical workflow.
Yep, correct. Yep, everything stays the same. You just do a little extra afterwards. Yeah. So it's very smooth like that. And then there's trade-offs. The one that people bring up all the time is statistical language. You have to get the model exactly right, whatever that means, for the inference to be unbiased and asymptotically consistent. Versus like if you're not too confident that you can model the outcome, what you can do is model the exposure, and now you're in the land of propensity scores. So there's a school of thought that's developed around these two approaches combined. And the idea is if I'm not confident in one, but I might be confident in the other, I'll choose the other one. But if I don't really know, I can use what's called an augmented or doubly robust or multiply robust method. That's essentially just a combination of those two, the propensity score and the G formula approach. And the idea is like those that suite of methods says I just have to get one of these fairly correct. So I get two shots instead of one. The pessimistic side of me thinks of it as two shots in the dark, but
Mhm. Mhm.
still two shots. So.
Yeah. Um, so I guess just between what you just said, and you said, some people might criticize you for also calling this all missingness. Are you saying that effectively there's some essentially dualism or duality between these two methods, um, in some way, even if we can't, even if it's not quite formalized yet, there is some interpressure where you by working with one effectively, there are implications with the other one.
Yeah, in a way, they're I don't know. Yeah, there's a duality in the sense that they both fit in the same framework. You can both state them using counterfactuals and potential outcomes. However, um, if my understanding is correct, wow, my imposter syndrome is strong on a Monday. Then the propensity score approaches rely on this missing data concept of there is a potential outcome under treatment and under control. The G formula framework, in my experience, in my opinion, does not rely on that. Like you don't need potential outcomes to understand that approach. You just need to understand the idea that you're replicating randomization. Um, and probably gonna get slammed for that too. But that is the way I understand it. And so there's a difference there. Yeah. So potential outcomes to me is the way I pitch it to myself and to people I try to explain it to is, oh, by the way, you could do a backdoor adjustment, G computation, and it's very smooth with your workflow for fitting models. But there's this other way. If you think of it as two potential outcomes, like a missing data problem, it opens up propensity score methods. Um, and that might be a more viable way for you to go, um, for example. So it's kind of a it's a place for me that's nice because it's where statistics contribute something. It says, hey, here's a statistics approach that you wouldn't naturally think of if you were modeling, and we're going to pull in stuff that we've worked on in survey sampling and try to recover like a causal effect, just like you would with this G formula method that works really well with your workflow. But it's yet another approach, right? Yeah.
What would out of curiosity, this G computation method, where are its intellectual roots, if you will?
Um, oh, this is where I'm bad because I go back to Jamie Robbins and Epi and Biostats.
Okay.
I think I think the G formula is his baby. It was named, I don't know if it was named by him or named in a paper that came from his key paper. He has these like three or four key papers. So I'll attribute it to Jamie. And beyond that, I my history escapes me for that approach. Oh, the other side of it is Judea Pearl. So in computer science, it's the same concept was developed. Um, I don't know how much back and forth there was though, because I know they talked to each other or they did back in the day. So, but he calls it the backdoor adjustment criterion, and James calls it the G formula or G computation. But it's essentially statistically, it's really elegant because it's the law of iterated expectations or the law of total expectations. That's true when X is randomized, and you just take that same exact form and pop it in when X is not randomized, and that's the G formula or backdoor adjustment. That's it. Um, yeah, at the core of it, it's a very elegant substitution that is conceptually the way you would say, how do we pretend X was randomized? So yeah, so that's the root of that. I do want to. I do. I'll, in like a few seconds, I do want to also give credit to two other buckets of work, which is one is matching. So the idea behind matching is again, let's think of all our confounders that could possibly influence the exposure and the outcome, and let's find a person who got the exposure and one who looks exactly like them as far as their covariate vector is concerned, but who got the control, and then let's see if their outcome changed. So that's matching. And then the last one is instrumental variables, which you can ask me about. I could try to explain it, but I haven't worked much with IVs. It's a econometrics method, very well developed. by them. Yeah.
Yeah. So actually, just to backtrack, the reason I was asking about the basis of this G computation was because I was wondering if it was at all related to G factor from psychometrics.
Yeah.
Um, and which just for people who aren't up to date on I don't know, psychometric work done in the 1960s or whatever, that effectively they would perform like multiple cognitive tests, for example, like what you might have for like an IQ test or skills test or something like that, or knowledge based tests, and that across different skill sets that they would test, for example, mathematical or abstract thinking or deductive, um, problem solving, things like that, verbal reasoning, that geospatial reasoning, that they would essentially have this suite of tests that they do, and then G factor would essentially be looking at the underwriting sort of latent variable, sort of that single principal component on that, and how things vary off those. Um, and I don't know, maybe it was just too much of a stretch, but I was just curious because effectively, to some level, it did seem like it's like I was just wondering if effectively the moment you're adjusting for those things, that maybe that's where it came from. But there's only so many letters in the alphabet. Maybe the G bit came in from
Well,
anything.
no, I love that question because I was trying to figure out where G came from in G formula. My guess, my gut tells me it's from generalization. And that
Yeah,
was, I think, the original, like Jamie's original concept. And I love it because uh, in a lot of that body of work, the exposure, the would-be treatment, randomized treatment, is often denoted as A, not X, but as A. And I think a lot of us thought it was treatment assignment, but actually it was because in the early seminal papers that Jamie wrote, if I'm not mistaken, the drug that was in question was AZT, so it was an A.
hmm yeah,
So it didn't have to do with assignment, but I think it kind of, like backronyms work. It took on that meaning, like, oh, it means treatment assignment, but really it was from the drug name.
yeah. That is interesting. I like acronyms. I like how we're able to reason back for an explanation. I think this is actually something useful because uh, in the machine learning, especially medical machine learning, we fall for this so much, where effectively we see some type of effect and we have some good reason to explain why it is. Like, oh, this is because of this.
Yeah,
And then we were, oh, wait, you coded it wrong. So then you correct it and
yeah,
change something. It's like, ah, no, this is because of this instead.
right,
And we're always able to sort of back explain a post hoc explanation.
right.
Yeah, cool. Matching. So, can you tell us a bit more about matching and how it fits into these other things? We have the G computation. Um, we have propensity scores. Where does matching fit into this sort of philosophy?
Yeah, so like for like fairly easy toy example I often use that a lot of people use is, sickness levels. So there's a drug that's out there for, helping you with your headaches. And out in the world, there's people who have various levels of pain already, headache or not. Uh, if you enroll folks in a clinical trial, you can randomize this new drug versus the standard of care and see what the average effect is between them. So save that sickness level out in the world, it affects how people whether they buy and take the drug or they don't. And you have like the people who are the more sick people buying and taking the drug, and the less sick people not buying and taking the drug. Um, and what happens is that what's happening with the drug, in fact, is that it really helps people who are really sick, who are really in pain. It really helps reduce their headache pain. But for people who don't, the drug doesn't really help that much. So if you just analyze that data, right, without doing any causal adjustment from the real world data, you would see that, oh, the drug seems to be really working, since most of the people you're going to see are the sick people who are buying it. Um, but in fact, if you were to evenly distribute them like you would in a randomized trial, you'd see like, the average effect isn't that great, because it doesn't really affect. Anyways, all that to say, there's three ways we've discussed three ways you can approach this in causal inference. One is propensity scores. You model what the chances of getting the treatment as a function of being sick. Um, Another is the G formula. You model the headache pain score as a function of getting the drug, yes or no, and being sick. And then the third way is matching, where you would say, okay, for everybody who took the drug out in the real world, let's find someone who's just as sick and did not take the drug. Okay. What's the difference in their headache pain scores after that? So effectively, see, here's the missing data part. I'm constructing a potential outcome. It's just I'm using two actual people. And the idea is there's only one confounder that affects both. If that's true, then as long as I can match, I can get rid of the variation in my outcome, in my headache pain. I can get rid of the variation in that's due to initial pain. Because I found somebody who has the exact same pain score. The only thing they're different from this other person is one took the drug, one didn't. So what's left over has to be the effect of that drug. So that's the idea behind matching.
Yeah. Yeah. I guess just to obviously mention the obvious thing there, if they match on one factor, are they actually matching? And if you have millions of patients, would you only find the very one who matches, or do you look across all patients who are similar to that and essentially try to find a matched average patient? Which then I guess gets back to the thing where you're using patients from essentially you're just using data, external data. What's the relationship between that? How do you make decisions?
Yep, yep. Yeah, no, I love it because now you're touching on the nuances of that method. So this is even beyond, yeah, initial sickness level is probably not the only confounder. So you're it's the same problem that all three buckets face. You still need to have all the possible confounders, but to your point, like using multiple controls to match to like one person. Say, for example, that you only have the people just who took the drug in your data set. You have nobody who didn't take the drug. So you need to use external data. How do I then use a matching approach? Well, then one way to do it is, like you said, to take the average of people who have like all the same sickness level outside of your study. That's, as far as I know, I think that's what the synthetic control method is.
Okay.
You're creating an average person that would have been a control using external data. Yep.
And the average person is a point, not a distribution. Is that correct?
I think so.
Okay.
I'm not sure though.
So sorry
Yeah,
for being
it might.
pathological, but you know why I'm asking.
Yeah. No,
Yeah.
totally. Yeah, yeah, yeah. But yeah, no, I mean that's great. Because again, to your point, yeah, you could exploit the richness of the distribution and say, here's the distribution of like one person who could be a control at any given point if they enrolled in the trial. Yeah. Yep. Yep. Yep.
Yeah, that I mean the matching bit seems it seems engineering to me, in which I say in the most like complimentary way possible.
Mm-hmm.
And so I get based on things like if I had to do something, the matching that's it's closer, for example, I think to sort of the bootstrapping way of figuring these things out,
Yeah.
which appeals
Yeah.
to me greatly because it makes the strengths and the weaknesses much more apparent in my belief. Is that
So maybe
I
so
might be
maybe
wrong? I've only
because
given this like a half a thought, so go
I,
ahead.
I know well, and I've been in this like deep enough where I'm like, well, it's obvious, isn't it? And maybe it's not. But I was gonna say one of the strengths in this case of the matching method is, guess what? Let's go back to propensity scores. What did I do? I modeled the exposure as a function of the confounders. What did I do in the G formula? I modeled the outcome as a function of the exposure and the confounders. In both cases, I had to model. In the matching approach, I mean, there's no explicit model. There's implicit stuff going on, but my point being, I didn't have the model, at least up front. So yeah, it is more. It's more. It can be more realistic in that sense, where I don't have to posit a model that needs to be somewhat accurate. But what I need to get right is how to perform the matching. Do How many people do I use to match to a somebody who took the drug, or vice versa? Yeah, more engineering type, concerns. I think.
Yeah.
Um, yeah, I
Yeah,
would
it's
say that's
interesting.
right. Yeah,
Yeah, I and just to be clear, when I was describing it, like the first thing I go to basically is a sort of the first path, like the first order approximation,
yeah,
where you say you have this external, you have plenty. If the data is cheap, you
yeah.
know, then that is I think something that you could jump to. You could be sort of drawing from those things. It wouldn't require, I think, a large amount of mathematics at least to have the first order approximate answer down the page. It might be totally wrong. Um, but you could have something on the page long before I think some of these other essentially by that time it take to work out analytical methods.
Right, right. And honestly, there's at least one organization, one company I know of, and I'm sure there's more that are banking on that approach where the pitch is okay for your clinical study, you would enroll, like twice the number of people to allocate to each arm. But one possible way to cut that down is to only enroll the people into your treatment arm for your drug, and then use synthetic controls from like rich data sets that you as a company already have to construct like a control part of your sample. Of course, that could be really fraught, right? It's like, well, how are you constructing those essentially simulated people?
Mm-hmm. It's like
Because
the
that's gonna,
healthiest people we can find, I hope.
I know.
You know.
Well, no, actually, I guess it's the opposite, right? You want them to be the sickest, so then you show them the
Oh no,
biggest.
the controls, you want those people to be like not budge, right?
Oh
Because
yeah,
yeah, yeah.
yeah, 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 yeah,
But
yeah. You
but yeah,
want
you
to,
go on because this is interesting.
yep.
And yeah, I bet that because actually I think we might know some of the same people who are working on these problems.
Hmm.
Because you know, well, just finding patients, period, is a marketable is a service, a
Hmm.
sellable service. Finding patients
Hmm.
and knowing where to locate them. And having that at the fingertips of clinical researchers is that's a thing. And you could also, having these synthetic controls, how to construct those in a way that essentially regulatory bodies will accept,
Yep.
um, and also that pharmaceutical companies will accept. Um,
Yep.
uh, that is a thing. Can you tell any more about that, or just talk off the cuff?
I think, just kind of spitballing, regulatory wise, I think a possible plus is that you have to make. I would think you would ethically you should be making your assumptions reportable at least to regulatory bodies like FDA, saying this is how we decided on these covariates to construct our synthetic control population. This is the method that we used, and be transparent about that. Um, One of the caveats is that if that buck stops at the FDA, then there's less accountability to the public. You could make an argument that a lot of stuff stops at the FDA because a lot of the general public won't necessarily understand. But I think it's a null argument because it's like, yeah, but the point is like I'm in the general public, I'm not an FDA, but I'd be able to understand it and critique it and get on Twitter if something, and sound the horn if something was off and I noticed it. So I think as long as we make those ideas public and educate the public about basically what is going on with how we constructed that population, then it can be a viable strategy. Um, and that's not even getting into, yeah, like the cost of doing that, and then how that compares to the cost of enrolling a double the size of your study sample. Sorry, one of the other ideas was maybe another plus is if it's feasible, then you might be able to sit like pseudo recruit from a much larger population,
Yeah,
right? Like, yeah,
yeah. So I
more
think that
representative.
yeah, I think probably part of the issue here is that we might be implicitly valuing uh, certain advantages of this that the average person who isn't like really hasn't wrung their hands over a clinical trial might not be thinking about, where effectively, patients are expensive and typically the kinds you want are rare. And if you
Yeah,
get back to the issue before we had, for example, talking about uh I don't, this probably isn't the exact example, but you can imagine in your own doctoral work where effectively you very quickly ran out of patients due to missingness and things like that. And in clinical trials, we very quickly run out of the types of patients who we intended to have at the very beginning, because they don't adhere and things like that. So much goes wrong. These small data problems are rife in the health sciences. And then if you take that and you add a rare event or a rare disease or anything that makes them rare, and I think one thing people don't realize is that, very much in my opinion, but I think other people back this up, that in the clinical space, it is very high dimensional. So it isn't as if any patient ever varies amongst two or three dimensions. They vary among thousands of interventions. A hospital patient, if you're in the ICU with a stab wound, you're different from the person who's in there from a bullet hole, who's different in there from a sepsis event. And yeah, you're all in the ICU, or you're all in the same ward. You might be lined up in a bed next to each other, the same IV, same vital signs being monitored, but the different dimensions of importance are vastly different. And in the clinical setting and in the clinical trial setting, those same things are there too. So effectively, anywhere where you can scrape a patient or, find one from out from under a rock and stick them in your study, those are the types of things that people really value.
Yeah.
What did I leave out of that? Sorry.
No, I think that covers a lot of it. Because I haven't been thinking about this either. So so I'm thinking like you're thinking right now with and getting ideas from you. But it's a great point about the broad term would be representativeness, right? Of your patient population. And the other things that are more ethical and helps you hit equipoise are yeah, if those are hard patients to recruit, then you're saving time, you're saving effort, money, pain and suffering of patients being on that control arm.
Yes. Yeah.
Yeah.
Oh,
So
and just another one that I think a lot of people like we tend to take for granted, but the typical patient who you're trying, and this gets back to the efficacy versus effectiveness, the patient who you're trying to help, the general patient population, is probably not the person who ends up in a clinical trial. The clinical trial folks tend to be people who are accessing and have access to essentially the clinical research community. The people who, if you're in essentially if you're an urban poor or a rural poor, or just frankly generally poor, um, your health outcomes are going to be lower, and you're probably going to have less access to be involved in a trial to begin with. Trials are many, and I'll probably get lambasted for this, but is that we're essentially experimenting on largely wealthy, educated people who adhere to these types of things. At best, those are the best case scenarios, while figuring out a treatment for people who never would have heard about that trial to begin with. And that's not to say that all the people putting in an effort to people who are inclusive in these things aren't doing work. Obviously they are, because there's a huge amount of work on this stuff. I can't think of a single drug company who doesn't say we are working as hard as we can to find more people, to funnel a wider range of people in for our trials. But it's very difficult, and hence why these things are useful, because effectively you need to be finding out how to get access to people, and how to experiment. I mean, another one, and this is super contentious, so maybe this will be the last episode that ever gets aired. But it's like when people talk about clinical trials with pregnant women, and saying, they say, oh, there aren't enough, we don't know enough about the effects of clinical medicine on pregnant women.
yep.
It's like, well, no kidding, because like, have you tried to get a pregnant woman to get involved in a highly experimental drug trial? No, they are some of the most protective, hyper aware, risk averse people that you'll ever encounter. These are the times when people, lifelong smokers, will stop smoking because they're having a child. If that isn't a bigger clinical intervention, I don't know what is. And so the idea that you're going to have these populations who inherently do not wish to be involved in high risk trials, um, and how are you going to get clinical data on them in comparison to that, to, for example, the challenge trials that happened around the COVID vaccine, where you just had people lining up saying, "Yep, yep, pop it in my arm." This was back in probably April, May, June of 2020, with a few months of it coming out, and people are just saying, "Look, if this thing is shutting down the entire world, and it's a high risk to the elderly and the immunocompromised in these populations like this, why shouldn't I, as a young strapping person, let them assess the risk score on it? Where effectively any adverse event I'll have will probably be less." Um, yeah. Anyway, I'm just yapping now, but you get the idea that there are inextricable challenges where it's not like we can just math away the issues.
Hmm. Yep.
Um, if you can't collect data on certain patients, you truly have no experimental data. There's no evidence. There's no empiricism.
Right.
Um, and yeah,
Yeah.
go on.
No, super quick on that. I love that because I first of all, this is the most talking about synthetic controls that I've done in a while, and certainly I haven't thought about it from this angle myself yet. But I, I think I do think that a little sort of it's not really pushback; it's more building off your idea. But
Yeah, yeah, yeah. Well, where I'm wrong, I appreciate it. Yeah, just let me know.
no, no, because I feel like synthetic controls are a kind of a way to math our way out, not our way out of it, but it's a way to math in more diversity, more inclusivity from those populations. I'm on the AS, I'm on the ASA Jedi Justice, Equity, Diversity, Inclusiveness Committee now. I'm actually chairing the professional development committee. but it's like it is I hadn't thought about synthetic controls as a way to improve diverse uh, participant pools. And it's like the halfway, right? Like to your point, the best thing would be to actually enroll participants, but if we can't for various reasons, some of them being like valid ethical reasons, a lot of communities have felt like they couldn't trust the system for
Yeah.
good reason, then this could be a valid math way to do it. Um, yeah, all the caveats that go on top of it, but still, it's like it's better than not doing it.
Yeah.
Is the equipoise argument?
Hmm. Yeah, I know.
Okay.
I think that's reasonable. I guess, being out here in North Carolina, one of the things that I tend to think about are essentially, we have like inner city populations, who are vastly underrepresented in our clinical investigations, with few exceptions. I mean, without going into like, there are certain diseases and there are certain clinical outcomes, in which they are typically like overrepresented, but very few and don't tend to get as much research. Very broadly speaking, please don't send me hate mail. No more than you guys already do. I feel bad if the hate mail stopped entirely. I think they didn't care. But at the same time, and then also think rural populations. uh Appalachian folk, things like that, where we have these rural populations. I think that's one of the things that people also forget are a very at need clinical community, and it's an interesting thing. For example, like if you're trying to develop a clinical product, and this is actually an interesting thing. It might be totally off base. I don't know. It actually is a little bit on this causal inference thing and counterfactuals. But imagine you're trying to develop a digital healthcare product, and well, who's going to sign up and help you develop that? Well, it's going to be all these research hospitals at elite universities with the high, you know, 500 publication professors, and they're super eager, uh, hyper stoked doctoral students, and they're extremely well trained nursing staff who are used to conducting clinical research and gathering data that is good for clinical research. And so you're essentially sampling data from this portion of the population that looks nothing like what the average small bed hospital looks like out in rural areas. And the issue is, once that algorithm gets applied to the real world, there's going to be all those small hospitals, all those areas to it where it simply won't apply. They aren't going to be as good at collecting the data. So it doesn't even just come down to these patients are physiologically different due to their economic circumstances or racial, ethnic backgrounds, their previous health habits and things like that. It could just be that the people collecting the data at these clinical observation points are not doing it the same way that they are at these elite institutions. And that is a massive thing. That isn't just something where you say, "Oh, we'll get better cleanup." It's like, no, it's night and day. And the algorithms that you develop, from the AI and the machine learning algorithms that you develop for patient monitoring and things like that, it's night and day what you need to work on, and it's very sobering. If you want to feel like a like hot, good at everything, Top Gun data scientist, do not work on clinical data of this nature, because it will just slap you straight in the face. Like, no, you're actually not good at this at all, and you need to go back to the drawing board.
Oh yeah, yeah.
Yeah.
I think to use that parlance, it's what is it, data drift,
Hmm.
or I think
Oh, so here's they call it model drift.
model
So
drift. Yeah,
model drift, but it should be data drift. Essentially, the model doesn't change; it's the data that changes out from underneath it.
right, right.
Yeah.
Yeah, yeah, yeah. Um, but on the other hand, the other thing is like perhaps there's this enriched model that has everybody that you want, right? And the model that you end up fitting is this more atrophied model that is more narrowly applicable because of this selection bias data that you have. So yeah, I mean it fits in again to the causal inference framework. It all comes back. I think Jennifer Hill said all questions are causal questions or something like that.
I don't know that as a fact, but I do know that Andrew Gelman has said that Jennifer Hill has said that,
Yeah.
and
Uh,
therefore I believe it.
so I'm gonna come clean and now recall that I know that because I watched that episode of your podcast
Yes.
with Andrew Gelman where he said that.
So
So that's what I'm quoting,
okay, that's good. It's better than you quoting me having heard him, having heard her say it.
right?
Yeah, yeah. The epistemic uncertainty has just like been closed one loop.
Yeah. Whew.
Yeah, cool. Well, we only have a few minutes left of your time. Um, I was wondering about they talk about these things called path analysis and causal discovery. Is that something that we should look into or discuss at all, or should I hop to the end where they talk about some of the connections between these different methods?
Probably to the end. That stuff is super interesting. I have almost zero experience with it except for basically what the concepts are and what the gist is. Um, yeah, so probably hop to the end. But it is important. Yeah, it's something that I've meant to dive into. Once I find if you find somebody on the show to that I could jump on as the third watcher and ask questions on who knows like causal discovery and DAG discovery, directed acyclic graph discovery. That'd be great.
Yeah, no, I've been wanting to more of these graphical statistics type talks. So you had one thing in which you had enthusiastically underscored and highlighted with the words yes next to it. Um, what was that? What was that yes idea?
Yeah, so in the last section, and they're looking forward. So the last section of the paper is what will be the important statistical ideas of the next few decades. Section one is looking forward, or looking backward. Section two is looking forward. And in that section, there's a sentence here. What will come next? Dot dot dot. The safest bet is that there will be continuing progress on existing combinations of methods. And the first one is the one I highlighted: causal inference with rich models for potential outcomes estimated using regularization. And I'm super enthusiastic about that because um, the causal inference methods that are taught or have been taught traditionally, they'll use standard toy statistical methods. So logistic regression, linear regression, generalized additive models if you want to get really wild. Um, but in my understanding and professional opinion, there's nothing in the causal inference framework that limits you to those models. It's all about how you handle the expectations, the expectation math. But the actual equation you plug into the expectation uh, chunks, you could use any model you want. And so for me, this is a yay because yeah, use a regularized model that you discovered, plug it into there. It's the causal inference component is the framework. It can be about the methods and the models, but for me, the core of it is about how you interpret and adjust your model findings. But use whatever model you want, which is why I completely agree with that. I think that's the way it's going, and that's the way it's going to go for a while, and it's a good thing.
Yeah, it actually reminds me a bit about a conversation we had with Adler Perot. That's Perot with two T's and an E. Previously at Columbia, and now I think he's in Switzerland. But he was working on chi-squared GANs for, I believe, synthetic patient generation. So effectively to do causal
Mm.
inference with deep learning architectures. And um, again, what I think is interesting about that idea, I know there's a lot of fluff and hurrah about deep learning. I think some of it's warranted, some of it isn't. But several things that are very interesting is one, like the architectures in these do make it very easy to switch out and test a variety of hypotheses. And the architectures also allow you to essentially, I think, simultaneously test and learn from multiple hypotheses. And by reducing these things to an engineering problem as opposed to like more of these modeling problems, I think that it overcomes one of the main practical humps that people have to get over in order to make inference. Now, am I saying that like one of these methods versus another is going to succeed or be better than the other? Like, I don't know. Like, I don't know those things. But still, getting back to what you're saying, like with these highly parameterized but regularized models, and now essentially just trying to figure out empirically what works. I think that's exciting. Even if the specific models that are going to work haven't been discovered yet, or in some cases they have been discovered, but we're busy looking at the wrong thing at the moment.
Yeah, I feel like also on a general broader note, building off of that, with a lot of these rich data sets now, personalized data, big data, even like big small data, for one person, it's generally an exploratory market, right? Not like a confirmatory market. We're still exploring the space to see what models work for particular people or populations. So while we're in the discovery space, why not just go all the way and work on those methods? In the meantime, also building ways to confirm that with new data. But the idea is that there are hypotheses that have yet to be generated. And that's kind of the market we're in with availability of data right now.
Hmm.
Uh, so
Yeah,
yeah.
actually, it reminds me of again something from the Gelman and Vehtari paper where they talk about how there's the paradigm of um where we basically we have a model and we know it works in certain circumstances, and the question is then, well, like we know mathematically and things like that, and then the question is, well, how can we expand it, and how do we get to work in new circumstances, and under what conditions, and where does it start to fail? um and I like that two things. One, because it gets very much back to what you said, but it's this beautiful sort of coalescing of both deductivism and sort of this empiricism as we explore the new space. I think that is very cool. And actually, it reminds me a bit of, actually, never mind, that's going to be a total side tangent, and I won't go into it. Basically, the Lakatos approach, where he talks about mathematical proofs and says, you start with something simple, and then if you want to say something more expansive, you do this, and if you want to do something more expansive, he talks about how the assumptions of a proof expand under essentially the grandeur of what you're trying to say. And
Mhm.
I know Andrew Gelman has read plenty of Lakatos. Um, and I thought that was interesting. Also, they mentioned Popper at the end. They mentioned Karl Popper at the end, looking
They
forward,
do.
which I think,
Yeah.
yeah, I think that's always a good sign. I wish that these philosophers of science would be more part of statistical conversations, because I think that they had a lot of wisdom. They have very good guiding points, regardless of whether or not they specifically got certain things wrong. Because I think that there's a lot of flack sent at, for example, like Popper and Thomas Kuhn for the things that they get wrong, as opposed to the massive things that they described really well and sort of got things on trajectory. Um,
Right.
it's like if you launch something out into space and you're off by a tenth of a degree, you're going to be off by a lot in the end. But still, you have to say, well, actually, they're only off by a little bit. And I think that these conversations about what has worked in the past, what can help looking forward, looking at these people and abstracting and thinking about the nature of scientific development is very useful. Um,
Yeah.
yeah.
Uh, I want to touch on that really quick. There is a highlight here. I did highlight that Popper mentioned, and then later on, I love this part because I have this conversation with folks at work too, where some of the methods we're developing, I've had to realize. I had this like visceral fear when I first started using them, like, oh, they've never been used this way. There's no like good theory behind this. I know this. This is like my bailiwick, my scope. And then it took me a while to realize, no, 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 but that's how it should be. It's like that means we're innovating in the right direction, and the theory on the math stat side has to catch up. There because then we're trying to better characterize what the variances are around this or how the estimator behaves. But it should be driven by that. And it says here, much of the history of statistics can be viewed as the incorporation of ideas from the outside. Our strength of the strength of our field, blah 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 blah. We can expect many of the new developments to come from other fields of science and engineering in the same way that earlier developments and stats came from within applied fields such as psychology and genetics. So it's something I think for any of your biostats listeners and watchers to keep in mind is that's the scope of things outside of that realm. It's we're trying to develop new things that won't necessarily have like tight theory behind them, which is totally
Mhm.
fine. That's the point.
Yeah. No, I really like that. And just to layer on that, I think it is one of the reasons why people like Andrew Gelman and Aki Vehtari, why they're so broadly read. They're so widely interested in things, and that's why people love reading about them so much. And on Andrew Gelman's blog, with all the vibrant debates, where if you want to talk to him, you just pop a message in his blog, and like, and you can have a question. And actually, I'll bring up one more thing that I think is really really interesting about this, and it shows, I think, the intellectual vibrancy of these two and the community that they're a part of, and that they've helped build too. Because I mean, it's hard to separate the vibrancy of the statistical intellectual community from what people like Andrew Gelman do. But right at the beginning, I wrote this is there's this like Apostates Welcome statement where he says the present review is intended to cover the territory and is influenced not just by our own experiences but also by discussions with others. Now here's the highlight bit. Nonetheless, we recognize that any short overview will be incomplete, and we welcome further discussions from other perspectives. So that's literally the first paragraph that they have. And then at the beginning, or right on their second last page they have this thing that says, this is page 2093, right side, and says, but in this article, we have attempted to offer a broad perspective reflecting the different perspectives of the authors, but others will have their own ideas on what are most important ideas for the past 50 years. And another view is gained by looking at topics and articles published in statistics journals. Oh, so it goes on. But essentially, I know this is an oversimplification, but it's like this apostates welcome where it's like, you can totally disagree with us. Let's have the conversation. And I think that is a really lively shot in the arm sometimes, where effectively things get so combative sometimes where we aren't welcoming of like outside, you know, contradictory but well thought out views. I think that's really cool, and that's one of the things I really like about sort of the community, Andrew Gelman's blog and things like that, where they're actively debating and conversing and things like that.
Right. It's like I think in my very novice understanding, I feel like it's kind of in line with I guess uh, my understanding of Tukey's approach, right? Like there's this cadre of like the academic statisticians who at the time were very focused on confirmatory studies, and he said, no, you forget that half of what we do, at least half of it is exploratory, and that's just not formal exploratory analysis. It's for exploratory scientific analysis. uh, uh, Night science and day science. As there was a recent article in Nature or Science that these two, I think they were biologists or something like that, explained it as night science versus day science, talking about confirmatory versus exploratory. But yeah, and to be exploratory, yeah, just like you said, and Gelman and Vehtari said, you have to open up the tent. It's not, you can have a big tent, just don't close the tent doors. I don't know what the analogy is here. Big tent, keep it open.
Yeah.
And I love that because I brought that up too and posted this on LinkedIn, and somebody, there was a rejoinder in the thread and said, well, I don't know, this is, one perspective on it. And I said, yes, thank you for that and for your input. That is in fact what they've said as well. So, yeah.
Cool. On that note, one of the questions I always ask at the end is, on the issue of different opinions and debates and things like that, what is one topic that you would like to see the scientific community or statistical community debate?
Debates.
Mm-hmm.
Ooh. Oh, I'm going back to my core, which is stats of one and N of one research. I think I would love to hear them, in the spirit of strengthening that field, debate the use of it, the use cases, where it's used, where it fits into a regulatory framework or doesn't. So not just the math of it as well, and the theories behind it, especially things that I'm working on. I'd love to get pushback. It's nice being one of the few people working on it. It's also very scary because it's
Mm-hmm.
like I don't know if nobody's checking my work.
Yeah.
I'd like people to check my work. If anything, it's like, please just shut me down. Like at least I know that somebody's working on this other than me, and I've teed you up to do something better. So that'd be great if people could debate N of one single case designs.
Yeah. At least point out if you like multiply by -1 somewhere in the equation,
Somewhere in
just
there,
like help me
right?
out. Yeah.
Somebody, I
Cool.
got the wrong index here. Oh
Yeah.
no, there goes my body of work. It's fine. Just somebody look at it, please.
Yeah. And he's like, there goes your body work. And some patient's like, oh, there goes my body.
Yeah.
Yeah.
Wah, wah.
Yeah. Well,
Well done. Well done, sir.
yeah. Cool. Well, Eric,
Uh,
it's always a pleasure. And I can't wait to talk to you again sometime in the future.
Same. Thank you for having me, Glenn. Always a pleasure as well.